In this video, we're tackling the 3 by 3 determinant. How are determinants used to find the area of polygons? The Bermuda Triangle is an area located off the southeastern Atlantic coast of the United States that is noted for a high incidence of unexplained losses of ships, small boats, and aircraft. You can estimate the area of this triangular region by finding the determinant of the matrix that contains the coordinates of the vertices of the triangle. A triangle has 3 vertices, so the determinant that's going to take to do that is going to be a 3 by 3. Determinants of 3 by 3 matrices are called third-order determinants. One method of evaluating a third-order determinants is called expansion by minors. The minor of an element is a determinant formed when the row and column containing that element are deleted. Okay, so the first minor, they got rid of the first row and the first column. The second minor, they got rid of the first row, second column. And third minor, they got rid of the first row and the third column. To use expansion by minors with third-order determinants, each member of one row is multiplied by its minor and its position sign. The results are added together. The position signs alternate between positive and negative, beginning with a positive sign in the first row, first column. So to do a third-order determinant by minors, they have A times its minor minus B times its minor plus C times its minor. Evaluate using expansion by minors. So we've got 1 times its minor minus 0 times its minor plus negative 1 times its minor. Now hopefully we're feeling pretty confident with the 2 by 2s now. So we're going to have 1 times 3 minus negative 6. I'm not even going to do this next one because 0 times anything is going to be 0. And negative 1 times negative 4 minus negative 4. So I'm just going to put plus 4. Oh, that's going to be 0 also. So all I'm going to have left is 1 times 3 plus 6, so 9. Okay, that was one of those. I think we could use another. We need to take negative 3 times its minor, and then minus 2 times its minor, plus 0 times, I really don't care what its minor is, but I'm writing it down for practice anyway, because 0 times anything is going to be 0. So I've got negative 3 times 4 times 6 is 24, minus 3 times 1 is 3, minus 2 times 1 times 6 is 6, 2 times 1 is 2. So negative 3 times 21 minus 2 times 4. So negative 63 minus 8 is negative 71. Another method for evaluating a third-order determinant is by using diagonals. First begin by writing the first 2 columns on the right side of the determinant. Next, draw diagonals from each element of the top row of the determinant downward to the right. Find the product of the elements of each diagonal. Then draw diagonals from the elements in the third row of the determinant upward to the right. Find the products of the elements of each of those diagonals. To find the determinant, add the products of the first diagonals, then subtract the products of the second set of diagonals. To evaluate we're using diagonals, first we need to copy the first 2 columns down again. Then we're going to find the product of all of the going south diagonals. Here comes my map analogy again. So we've got 9, 0 times anything is 0, and negative 1 times 2 times 2 is going to be negative 4. So that sum is going to be 5. Going north, I've got 1, 0, And negative 3 times 2 is negative 6 times negative 2 is positive 12. So that sum is 13, and then I want to take the south minus the north, so 5 minus 13 is negative 8. Okay, another one like that. I think we could use at least 2 to practice. The first product, 2 times 0, oh, stop, the product's going to be 0. Negative 3 times negative 2 is 6, times 1 is 6. And negative 1 times 5 is negative 5, times 2 is negative 10, so that sum is negative 4. Going north, I've got 0 plus 2 times negative 2 be negative 4, times 2 be negative 8. And 5 times 5 is 25, times negative 3 is negative 75. So that sums negative 83. And we're going to take the south minus the north, and we get 79. Here's one application of 3 by 3 matrices. The area of a triangle having vertices at A, B, C, D, E, F is absolute value of A, where A equals 1/2 the product of that determinant. Notice that it is necessary to use absolute value of A to guarantee a non-negative value for the area. We don't have a black hole here. Find the area of a triangle whose vertices are located at 0, negative 1, negative 2, negative 6, and 3, negative 2. This is not a nice, pretty right triangle, so having a formula we can just plug and chug into is nice. Now we get to decide, do we want to do minors or diagonals? I'm kind of liking the minors myself, so I'm going to go that direction. So I'm going to have 1/2 times 0 times its minor. So negative 6, 1, negative 2, 1, minus negative 1, so plus 1, times its minor, negative 2, 1, 3, 1, plus 1 times its minor, negative 2, negative 6, 3, negative 2. There's not much practical reason to evaluate that first determinant because 0 times anything is 0. 1 times anything is itself, so all I need is negative 2 times 1 is negative 2, minus 3 times 1 is 3, plus 1 times anything is itself, so negative 2 times negative 2 is 4, minus 3 times negative 6, so minus negative is a plus 18. Just carrying that 0 wrong for general principle, it's not serving any purpose. Negative 2 minus 3 is negative 5, 4 plus 18 is 22, so I've got 1/2 of 17 is 8.5, and they didn't give me units, so I have to call it just units squared. The authors of this book must have preferred the minors method of doing 3 by 3s for determinants as well, because that's what they focused on in the summary. And the area of a triangle with vertices at A, B, C, D, and E, and F is given in the summary as well.